her amazing work, and now it's welcome Raquel to start her talk.
Great. Thanks for the kind words. Sorry to cut you off. Anyways, it's always embarrassing, these bios. Cool. So it's a pleasure to be here today, and it's been a great CVPR so far already. I haven't been in a conference in 4 years. There's two things that happened. There was a pandemic, and then I founded a company. So actually, I was pretty busy, kind of building the foundations of that company. And in this CVPR, we are unveiling a lot of the great technology that we've been developing, and having a lot of really exciting research that actually is not just research that is cool, but actually is what empowers our production system that we work every single day. So it's been an incredible journey, Wabi, and definitely something that is the next level in terms of the quality of the research that we do, because everything that we do really works, and I really mean it. Cool. So today I'm going to be talking about simulation in particular. But before I get into simulation, let me show you our cool robots, okay? And hopefully this internet works, which we were having a lot of trouble before. All right.
That means safer roads, a stronger supply chain, a new era of logistics. At Wabi, we believe that to unlock this new era, we need to build the next generation of technology. Meet the Wabi driver. Powered by our AI-first approach, the Wabi driver is ready for trucking.
This is not rendering, this is our true robot.
The Wabi driver has two components: the advanced virtual driver as software, together with sensors and compute as hardware. It includes LiDARs, cameras, and radars for increased redundancy and safety. At its core, the Wabi driver is a full autonomy stack. From sensing the world to decision-making, the entire system as a whole automatically learns from data. Thanks to Wabi World, our groundbreaking simulator, we're able to expose the Wabi driver to the vast diversity of experiences needed to hone its driving skills, which would be impossible otherwise. This makes it safer and smarter before the wheels even start turning. The Wabi driver is a single AI system that is both modular and interpretable, which means we can trace every choice it makes and we can validate its decisions. The Wabi driver has superior generalization capabilities. It can apply learned skills to new situations and geographies it has never seen before, unlocking new autonomous routes with unprecedented speed. We built the Wabi driver with production intent from day one. It's designed to be easily integrated on the assembly line for a safe, reliable, and scalable product. And it's highly flexible, adaptable to multiple redundant truck platforms and sensor configurations. We are unveiling a new paradigm, safe, scalable, and ready for the road. The future of trucking is autonomous. The future of trucking is here.
Cool. So this is what, I've been pretty busy the last 2 years, which is building this amazing first generation of robots with this Class 8 trucks, as well as the simulation system that really empowers us so that we can train the system, test the system, so that when it touches the road, it's really performant. And in an undisclosed location in the US, you can actually see the robots driving autonomously on public roads. So something really exciting. All right, so let's get into the meat of the talk today. And I thought that although this is probably obvious for everybody, it's always good to start by, okay, what is self-driving all about? And then how simulation can play a role in this. So if you think of, how almost every single software stack in self-driving works, is that you gather information from the sensors, right? Whether it's LiDARs, cameras, radars, etc. And the first thing that typically these systems do is that they localize the vehicle with high precision so that you can use high definition maps, which you need to use these high definition maps as sensors because they are not perfect. There might be changes that you see in the environment for construction and other things, for example. Right? Then basically you need to perceive the world around you. You need to be able to predict what the different actors are going to do in the next few seconds. And then you use the information about the past, the present, and the future in order to decide what is the safe maneuver that you need to execute in order to drive safely, right? And then you repeat this process every fraction of a second. The last bit that you typically have is control, where the idea is that when the motion planner, you try to execute that plan, but the vehicle does slightly different things because you don't have the perfect vehicle dynamics, because you don't know everything about the coefficient of friction of the, of exactly where you're driving, etc. So basically, you need to have this last module that is steering the vehicle towards the plan that you intended to execute in the first place. Right, and this is, as a whole, something that you repeat every fraction of a second, typically every 100 milliseconds. In, as I said, almost every single self-driving system. All right, so we've been at this for many years, and as an industry, since the DARPA challenge is almost two decades ago, and despite so much effort, so many billions of dollars, we're still far from commercialization at the scale. And the reason why it really kind of boils down to statistics. And what do I mean by this is that if you look at, the situations that you need to handle, there is some situations that happen very, very often. For example, following your lane, right? And that's a boring situation, and that's great. These days, you can actually do that pretty well. But there is many other situations that happen really rarely. And what this means is that there is a very long tail, and there is a lot of mass on that long tail. And that's what makes driving really fun. So I have here some exciting pictures and whatnot. And I have to say that I've seen instantiations of 4 out of the 5 pictures. I haven't seen the elephants yet. Maybe I should go on a trip. But for example, this vehicle there, the aluminum-like vehicle, is a picture I took just walking around Toronto. And if you have a camera-based system, that thing is going to cause trouble, right? The other thing, things like birds is something that in BC here, it happened quite frequently. And this thing over here, this kind of like house, so you see a truck that is carrying a house, and you probably think this is very rare. It turns out that the first time that we engaged in autonomy at Wabi in public roads, we saw a whole bunch of those. And that was kind of interesting to see, like, how many of these rare things actually happens once you actually are trying to drive autonomously, right? So that makes the problem pretty hard, and it makes the problem hard in 2 ways. It makes the problem hard for autonomy that is in charge of driving safely, right? Because now you have to handle, your generalization abilities have to be really good, and that's, as you know, for both machine learning systems as well as for rule-based systems, this is actually a pretty hard task. And the second thing that is that if you want to test the system to really say that you're ready, for example, to drive autonomously, you need to test so many things, and that's actually really hard, right? Oftentimes people go on the road, right, millions of miles, but you're going to see a tiny fraction of that long tail. So potentially you need to drive even much more than that, and just for a particular one software release, right? So this is not sustainable, it's not the safest solution, and it's extremely capital intensive. So we need a better way to do this. All right, so simulation obviously is the alternative, right? That if we don't want to just drive on the real world, these empty miles over and over, right? We can try to build simulation systems where we can test, the software stack prior to deployment. And if we look at the industry today, there has been, I would say, like 3 main sources or types of simulation that you will see. And companies typically have many tools, many simulation, different types of simulations and whatnot. Simulation systems, sorry. And that's actually not a good thing. It's actually better to have the simulator, and I will show you in a second what that means and what we can do. So the type of simulation that is most used is what is called log replay, which I'm not even sure why it's called simulation, right? But this, the idea of this is that you capture data in the real world, and then you just replay it. And then you're gonna just use the sensor information in order to see how your system kind of behaves. And typically you can do it in open loop where you're not executing your maneuvers, right? Because if you execute your maneuver, then suddenly the sensor data will be different. So you can use just replaying that log, right? So that's, and then what happens if you try to, if you are still kind of trying to execute your plan, is that you end up with collisions and things that are not very realistic, right? So this is the most used source of simulation, but is, as you can see, is very primitive, and it gives you a signal, but it doesn't give you a lot. Something that is also very used in the industry is behavioral simulation, with the goal of testing the motion planner. So the idea here is that you're going to generate a lot of scenarios and things, and then you're going to create your abstractions of those, which are typically bounding boxes, trajectories, whatever, that you pass as input to the motion planner, and then you test how the motion planner reacts in that simulation. So this is closed loop, so that's better, but you're only testing a small part of the software stack. What means is that you are not going to have a full understanding of how errors in perception and prediction will actually confuse the motion plan, right? You have this overly optimistic view of the world. And as a consequence, you also can't really see a lot of the potential mistakes that you will see in the real world. Okay, those are the reasons why you still see companies driving millions and millions of miles. The last bit of simulation that you don't see that much in the industry yet, or there is very, very small use cases, is the use of game engines, for example, to generate synthetic data so that you can train and test perception systems. So this is typically employed only for rare things, like let me simulate, for example, fire trucks or things that I don't have a lot of examples on my training data. But it's not really used at large for the full perception system. And the reason why is that it's not very, very realistic. And typically these environments are built by hand. Artists generate them. And if you want a realistic environment, just one of these scenes typically costs $100,000, $200,000. So that doesn't scale. Right? So that's also not a great solution. All right. So what we're going to try to do today is I'm going to show you, the kind of things that you need to do and some solutions in terms of how we can create a simulator. We're going to call it Wabi World, where you can really test at scale the entire system in closed loop and in a way that is near real time. It's actually pretty efficient, so you can run on the cloud, many scenarios as well, as many as you would like. Okay, so we're going to invert this pyramid of using a bit of using a lot of simulation that gives you a little signal, and then you go on the road and you do a lot of road testing, to where you basically do most of your development on simulation, and then the road is mostly verification, validation and verification. So it's a very, very different approach, which is what we have done at Wabi from day one, is build this amazing simulator and then really empower everything that we do this way. All right, so let's look at Wabi World engine and the kind of things that it needs to do. So it's going to be closed loop, which means it's like a video game. That doesn't mean that it has a renderer that is like a video game renderer. Okay, so this is not Unreal or anything like this. It's going to be something else, but it has to be reactive, right? The world reacts to the self-driving vehicle, and the self-driving vehicle reacts to the world. It also has to be immersive. What do I mean by this? Is that we need to simulate how the sensors will have observed the scene so that we can test the entire system, right? So we need to generate camera data, radar data, lidar data, etc. The same way, with the same fidelity as the real world. So it's reactive, right? And we need to generate at the scale and diversity of the real world, right? Remember all these long tails and whatnot. So we are trying to build very scalable solutions where we can really construct worlds to a scale that was never possible before. All right, so what you see over here is kind of like a block diagram of how the simulator works, and it's very simple, right? You have your world state, given that, which basically is where everybody is, your scene as well as yourself, right? Yourself meaning the self-driving vehicle, and then you're gonna render how that self-driving vehicle will have observed that scene. Then you're gonna give that information to to your software stack, right? The same as if it was the real world. You're gonna execute, everything there, and that's gonna give you a maneuver that the self-driving vehicle wants to do. And at the same time, you're gonna do a tick of executing that maneuver. Then you will have the world that is gonna react to you, given the change that you have in behavior, and then you're gonna update the world state. Okay, and this thing just continues in closed loop, right? That's the way that you have reactive actors to you, and then you are reacting to the actors. Okay, so very, very simple concept per se. And the other thing that is important as well is that, because we're gonna run this at the scale, is that you need an evaluator that is able to automatically give you metrics in terms of how well you are doing. Okay, there is a lot that goes into evaluation and metrics. I'm not going to talk about that at all today. All right, so So this is Wabi World, and let me know if I'm speaking too fast. I'm getting too excited. All right, so what Wabi World, what you can see here is that, right, so it's gonna be built in a very simple concept, which is that the world is out there and it's amazing. Why do we need artists to recreate by hand the world if we can automatically reconstruct the world in a way that is, you can manipulate it? Then suddenly you have the skill, the diversity, and you have the ability to really test in places that where you're actually intended to go in the first place, right? So that's a very simple concept, but it's very, very powerful. All right, so we're gonna be able to reconstruct the world, simulate the sensors. We're gonna have sophisticated behavioral models. And not only this is gonna be a way to do testing, but also it's gonna be a way to learn on the simulator. And you can learn any piece of the software stack that you want, okay? But you can learn from the end task. Even if you are, for example, only interested in learning perception, you can still learn perception so that you drive the best. So it's a very, very flexible way to do this. All right, so I'm gonna first show you stuff on a scenario generation, and then I'm gonna show you a lot about reconstructing these digital twins, and then a little bit about coverage analysis and safety case. Okay. All right, so let's talk about more of the behavioral aspect that most of you are familiar when I say simulation, right? So the task here is the following, right? You want to do simulation, right? You want to create scenarios that are and actors that are reactive. It's actually twofold. So given a high definition map, the first thing that you need to do is generate a scenario that is realistic. This oftentimes in the self-driving community, in the computer vision community, is a task that is totally ignored, but it's very important. This is scenario generation. So that they, if you're looking for a problem to work on, that's actually an interesting task, very important task. Anyways, but you're gonna specify the scene, and then given that scene, the second task is to unroll a policy for a very long time to have realistic behaviors. Okay, is that clear? Right. All right. So let's see how we can do the specifying or generating the scenarios in the first place. And then let's look at how we can simulate the behaviors of the actors in a way that is controllable, diverse, and that works really well. All right, so if we want to generate these scenes, right? So we have an empty map, and now we need to place traffic, right? That's the idea here. So we want this to be efficient, right? So that we can generate, billions of scenarios, right? To do our testing. It has to be realistic, right? Because we need to test things that are going to happen in the real world. It has to be diverse, right? So it's not about having high likelihood, but also you need to cover, all the long tails. And it has to be controllable so that whether it's the machine or a human, for example, safety engineers are able to kind of play with the scenario generation to create the scenarios that they want if they are interested in particular things. All right, so there is many types or different, I would say 4 types of ways that you can generate these scenarios. And with Wabi World, you can do a combination of all these different things. One that is being very, very popular for self-driving, particularly when you talk to system engineers, is to have manual creation of those scenarios. And by manual, I don't mean the GUI where you drop things and you move around. I mean a way that programmatically typically create those scenarios, okay? And that's a very traditional way, typical way that you can do these things. So you can think of, in the context of generative AI, you can think of this, your prompts that you want to generate those scenarios. And in general, right, so you have controllability, but it's hard to make, to specify everything for a scenario, right? So it's actually pretty limited, typically, the way by manual creation. Then some companies are looking at creating procedural models of, which typically generate simplistic traffic behaviors or scenarios where the idea is that you have some kind of a little grammar with some parameters and you just sample from it. Okay, and that's the way that you can generate a lot of things, but you don't cover the long tails that way. Other things that you can do is, digital cloning, right? This is what I was advocating for before. So you can use, for example, auto labeling, right, to generate from just raw data automatically scenarios. And that's a concept that is actually very, very useful. And one of the things that you're going to see in a second is how we can use this to this concept of digitally clone to also change what we call mixed reality, which is you can start with a scenario that happened, but you can modify to create variations that are more interesting or asking questions of the what if. And the last bit that, I'm sure that some of you are very excited about is, well, with the boom of generative AI and whatnot, you can actually create generative models to generate these scenarios. And this is, one of the generative models we created a couple of years ago. But you can mix and match the way that you can do these things. So in Wabi World, you can specify scenarios, you can create them from real logs, you can modify them, or you can fully generate it automatically, thanks to our generative AI technologies. All right, so what kind of things you can do to generate these scenarios? So yes, I'm going to give you a flavor of some of the things that you can do. So a couple of years ago, we built, for example, methods that you can iteratively unroll the scenario, right? Where you can generate with RNN-like thing, right? One actor at a time, and that actually worked pretty well in practice, right? But is not the most efficient method, and it's not controllable, which is something that we really would like to have, the ability to really specify more things or be able to say, for example, we want to generate actors in this lane or things like this. So from that, we have actually moved into something that is more exciting. And I guess without saying what it is, it's something where you can actually generate full scenes at once. So it will be much more efficient, right? But at the same time, you can also add things, you can remove things, and you can control and specify constraints of the kind of things that you want to do. So these are just generations of the model, if it's unconditional, right? And then you can condition in all sorts of things during test time, so that you don't need to learn for every condition that you might want to do in the future. In this case, for example, we are saying, okay, this is the region of interest, generate stuff only there without colliding with any of the other actors that are already in the scene, right? So you can see like an easy way to edit and create things if you're interested in particular scenarios. Cool. So that's, certain ways that you have generated scenarios, right? And then let's assume now that we have those scenarios, and now we want to control those actors in a reactive way that is very realistic and is controllable. Okay, so let's see how we can do this. And I will not go a lot of the details, but I will give you a flavor of the type of methods that we have developed. And in particular, I'm going to talk about one of the papers that we have here at CVPR, which is an interesting, I will say, approach, where the idea is, again, that you can create these digital twins, but then you can modify them to create all sorts of stuff and really answer the questions of what would have happened if it turns out that this vehicle will have accelerated, will have been more aggressive, etc., which are things that are really, really useful to answer in self-driving in order to really understand the robustness of your system, for example. All right, so let's look at how we can do this. So in particular here, the kind of technology we unveiled at CVPR is a hierarchical model. And this particular model is actually fairly simple in terms of the hierarchy. You can build, much more sophisticated hierarchies. But the idea here is that the first level is going to control the route. And it's going to be a really interesting way to incorporate much more efficient, for example, search space, as we're going to do some stuff with it. And then condition on the route, then you can actually create your, you can enroll your policies, which is stochastic, in order to create scenarios. Okay, so it's a fairly simple, I would say, two-level hierarchical model. All right, so and then I'm going to show you some of the properties of this model. So it's going to be controllable, you can generate things, and then you can create adversarial examples as well. Right, so let's see how we can control this. So the control is very, very simple, right? So you can, this is where you want to build reactive log replay, right? So take that concept, all concepts in the industry are just replaying logs, and now let's make everything to be reactive to you, right? That's something that is very powerful. So the way that you can do this with this model is that the first thing that you need to do is infer the route for every one of the actors. And that's something that you can do through optimization. And then condition on that you can enroll the policies, but now the actors are reactive to each other and they are reactive with respect to the SD. Okay, and that gives you a full simulation system where now the logs have variations with respect to what really happened in reality. And it turns out that this actually works much better compared to other ways of doing simulation, where from simplistic IDM-like models to things like behavioral cloning to closed loop training of imitation learning. That's what the IL path stands for, etc. So it gives you much better realism, as well as much better kind of common sense metrics, like not going off the road and then driving well. All right, so let's look at how this works in practice. On the left-hand side is log replay. The SDV is closed loop, but the actors are not reacting to you, so the test is kind of invalid after a bit because you're going to get into a collision, right? Because the actors are just dumb, right? They are not changing. The right-hand side is mixing, right? So now everything is reacting, so you can actually unroll simulations for much luck. All right, so now you can compare also to all these other ways, and you can see, hopefully the video plays, you can see that you have much more natural behaviors by doing something else. Compared to the other things stop when there is a collision, okay, because there is no more reason to continue the simulation and you have already collected. All right, that's the one that listen to me anymore. All right. Cool. So now let's look in. So in the controllability side, right, we were reconstructing a route and then being reactive. Now we can just be purely generative. So the idea here is very simple, right? Is you're going to sample paths on a link graph. That's how you get, your routes. And then given each one of the samples, then you can sample your policy, right? And that's the way that you can get, many variations, right? So let's look at how this works. So this is just showing a log that was captured in the real world, and replays on the top left, and then just variations by sampling the stuff, sampling different routes that you have. Okay. So everything is stochastic, so you can get many of these variations, right? So it's a very natural way to do this. And now we can play also adversarial, right? A couple of years ago, we had this paper, adversarial sim, right, where we were attacking, we were looking at changing the kind of bicycle model parameters so that you can create scenarios that are adversaries, but it wasn't like super realistic. So thanks to this hierarchy, you can have, you can look for adversarial scenarios in a much faster way, and they're also much more realistic. So that's a much better way to get kind of like corner cases for your behaviors. On the left-hand side is just attacking using as parameterization so it's the same attack, but using as parameterization the bicycle model, right, of the actor. And on the right-hand side, we use the routes, and then the policy is just unrolling. Okay. And you see that you get much more interesting behaviors, like, for example, here the bus or truck is actually getting, nudging to us, and then we're going to get to a collision, right? So much more natural things that in this case, we see that this particular planner, which is a bit of a dummy planner, has difficulty, so you can attack it easily. Cool. So when you build all these behavioral models, I just show you one here with Mixim, but something that is very important as well is that your simulation shouldn't just have a particular type of agent, right? Because the world, as humans, we behave so differently on the road. So you need to be able to test against many different policies. And that's why we have what we call an actor zoo, where basically, and this is just some examples, where basically you can actually, every single agent, you can decide, which policy you sample from. Okay? So that you can, this way, you can create so many interesting variations of the world. Cool. So now we talk a lot about behaviors, and I'm going to talk about appearance as well as sensor simulation and creating the 3D digital twins, not just the behavior part of it. All right, so let's go into Unison, which is one of them, I guess, probably the best paper I ever brought. So let's see what is the idea here, right? So I mentioned that before as well, which is, for 3D content creation, typically in the industry, you have artists. And then what you will see is like there is only a couple of scenes, right? Because it's very expensive, right? So now we're going to just digitally clone the world by creating a variation of Nerf-like thing where you can actually get like really good results that are controllable, editable, which is the thing that is key here, because not only we want to clone the world, we want to modify it and re-render everything, right, from the perspective of this closed loop simulator. All right, so it has to be manipulable, which is something I can't pronounce, all right? And so we're gonna do things like not only reconstruct and do log replay, right, within the same simulator, we are also gonna do actor removal, actor insertion, we are gonna manipulate the trajectories of the actors and other things of the actors, and we can manipulate as well the self-driving vehicle because it's a closed loop simulator, so it's gonna be a different trajectory than whatever you observe when, with that original data that created the nerve. All right, so without going into too many details, right, but the idea is, I would say fairly simple, right, is that you're going to treat a bit differently the static part of the environment, all the dynamic actors, right, because the static is just static in the sense that 3D world is not going to change, but the actors that you have inside, we're going to do all sorts of things with them, right, so we have to decouple these two things. And you can use in this case as input, we're going to have LiDAR and camera, right, capturing the scene, a single log, right, a tiny snippet from that, we're going to clone that world. And that kind of anchors, where to look at in terms of where there is LiDAR points so that we have a sparser world to look at versus having to voxelize everything in the world, which is, too much in terms of the dimensionality. And in particular, we're going to use a multi-resolution neural feature grid in order to represent every one of these things. And it's something that actually works pretty well in practice. So how we're going to render with this is that, given a location of the SDV where the sensor is, right, and the particular ray that you're interested in rendering, right, so we are going to basically perform volume rendering, but it's going to be volume rendering at the feature level. So that we have more flexibility, and then that enables us to support smaller dimensionalities or bigger voxels, so that everything works out in terms of memory and computation. And then we're going to use a mixture of putting together two concepts, which is kind of a volume rendering together with image rendering, so that you have the best of both worlds. So you have this really high resolution simulations that you're going to see in a second. We can do the same thing for the LiDAR as well, where basically we're going to also volume render and use an MLP for the intensity, because intensity is a little bit more sophisticated, right? And in terms of the actors in the scene, the way that we're going to do this is very similar in terms of, we're also going to have these feature representations, and we're going to use volume rendering of those features. But the difference is that because you observe only a small part of the actors, right, as you have a little snippet of data, right, and we're going to need to render them from many different variations, potentially many different viewpoints, we are going to have kind of a shared representation by using a latent space and a hypernet, so that we can learn a prior of different objects in the scene from that one little snippet and nothing else. All right, so that's in a nutshell how it works. And now I'm going to show you results. And this is the part that if you were sleeping, wake up, because this is really cool. All right, so first I'm going to show you log replay, right? Left-hand side is the original log. And this is the only thing we have, this tiny snippet. And from that, we have to reconstruct and do all sorts of things with it. And as you know, this is, a single, line trajectory kind of thing, right? If you work with nerve, it really struggles to generalize viewpoint. But we need to create something where that struggle is not there anymore. So all this kind of stuff that I was talking about before enable us to really do so. All right, and so on the left-hand side, sorry, there was the original log, and then on the other side, you see the digital twin. Super, super realistic, but this is, relatively easy, right? You have seen things of this with nerves and other things, right? And the interesting thing is that this thing enables us to render in a cohesive manner both all the sensors, right? So this, I'm showing you here how we can render as well later, right? So we have multiple LiDARs, multiple cameras on our tracks. You need to render everything, right, together. Now we're going to play and change reality. Okay, so left-hand side is the little snippet of data that we have. Right-hand side, we're going to re-simulate the world. And in this, what I'm doing here is removing everything that was moving. Okay, and then just simulating how the scene would have looked like if we just drive here. And again, this is the only thing that you have to create this from, right? So it's pretty difficult in painting as well, kind of thing. So it works really well, right? And it turns out that you can do this with all sorts of different scenes. You can do this at scale, right? And oftentimes people ask me, does it work at night? Does it work with this sun is shining in front of you? And what you can see here is that it works really, really well. And oftentimes I show this, and I ask the question, which one is simulation versus the real world, right? And it's really hard to say. Everything is simulation, really, really high fidelity. All right, so now we can also insert actors. So I don't know if you see my mouse, but this guy over here, hopefully you see, is actually somebody that was never in San Francisco before. So now you can drop actors, and then, with the stuff that I showed you before, you can generate the trajectories, reactive, all the stuff, right? You can, insert many different actors. In this case, I'm just showing, a set of actors that come from a different log, but they are doing the trajectories of the actors of this log. Okay, so you see how, you can, by observing a bit of the world, suddenly you have so many things that you can do. And now we're going to manipulate them, and we're going to change their behavior as well to create, maybe more hazard-like situations. Original log on the left, and on the right, now the white car is aborting the left turn, and it's actually coming to our lane. Okay, and now we need to typically, brake, otherwise we will actually end up in a collision. Right? We can swap actors into who is doing what, right? And that's quite interesting because you can look at the effects of shape in your perception system, for example, but now in closed loop, all the way to the system level metrics, right? Something that was impossible before. You can continue modifying the behavior, and this is just another example where, this actor is lane changing and whatnot, right? So you can decide. Again, you can use what I showed you before to do all sorts of different behaviors and whatnot, and just render them with this. Last but not least, it's not play. This place, you can modify also the self-driving vehicle, right? And in this case, I'm just going to show you render when we are actually performing a lane change, right? Where now the viewpoint. In this case, I'm just showing for the demo, right? Just fully changing the camera and now showing the world from a different lane. This is where Nerf does a terrible, terrible job, right? But here you can actually really go and extrapolate viewpoints really, really nicely. And you can do this at the scale in all the different logs and things that I showed you before, right? Where now you can change lanes. You can also change the perspective up and down, and this is how we can, every single data that we ever capture with any platform can be used to train our trucks and to test our trucks. We actually use this technology to select where the sensors are in the first place in our truck, so that is optimal for driving well in the real world. All right, oops, okay. Great, so now let's put all together, and then we're gonna do closed loop. I'm gonna show you just some examples of now everything where we are actually going to drive in this virtual or mixed reality world using an autonomy stack. And the system is really, Wabi World is really configurable. You can use any autonomy stack that you want to. And obviously the autonomy stack I'm showing you here is not our production system. All right, so what we, in terms of the autonomy, right? The simulator is our production simulator. All right, so what you see over here is a log that was originally captured and whatnot, right? And now what I'm gonna show you is where now autonomy is driving on that reactive log. Right, you see that now autonomy decided to change lanes because we inserted this adversarial actor that is coming in the opposite traffic, right? So you see how you can generate these safety critical situations, right, with a level of fidelity that was impossible before, right? And this is just some examples, right, for you to see the power of what we have here. All right, that's another example, and hopefully you can see together. Oops. Same idea in this case, the vehicle decided to change lanes and then queue behind instead of, because the white car was actually coming into our lane. So it was, it's trying to be conservative and then let that vehicle get into the lane. Yes, that's another example of how you can do this reactive simulation in this real world, mixed real world. All right, so that actually works really well. And what is interesting is if you look at the metrics, in this case, this is using only the camera-based simulation. You have that the domain gap, in this case, we are showing perception, is actually pretty small, where if you train on real and test on real, you have, almost 41%, right, in this metric. And if you do it with our simulator, you get, only 1 AP less in terms of a perception-based system, which is, it's really, really, I would say, next generation in terms of how realistic this is. And then what is more important is that you can play the same thing on the lane shift situation, right? Which is where now you need to really extrapolate. And that's where, these other techniques, some of your, favorite techniques really have trouble. And, Unison really generalizes much, much better than anything I've seen before. You can use also for data augmentation by using the same logs, but augmenting by looking at different perspectives. And it turns out that you can actually improve even with the same data, just by doing this fancy augmentation this way. All right, and this works, in all different scenarios, different types of cameras. What I'm showing you here is if you actually, do the same thing now with lower quality cameras in highways. Just a different example. And we're just changing perspective from this was captured with a car and showing you what a truck would have seen. You can remove things that were there. You can add stuff that was never there. Right, you can do this in a continuous manner for, as long as you want. And this is the operation domain, potentially, not this particular one for us, but imagine if you capture in your operation domain, you can actually have simulation exactly where your vehicles are operating, which is also something that people don't have in this closed loop simulation. So it's really a new concept in terms of all these things that you can do with this Wabi World. All right, maybe on the last 1 minute I have, I'm gonna just talk a little bit about the last bit, perhaps, which is that, all this great, but the last bit that you need as well is as you go towards making your safety case, etc., is that you also need to start incorporating this notion of coverage. So this simulator is, a big piece of our safety case, but now you need to also understand which scenarios with which frequency do I need to simulate in order to really, if I do well on those and my domain gap is very, very small, I can actually say that with very, very high probability, I can handle all those situations in the real world. Okay. So the last bit of some of the things that we are looking at, just to give you a flavor, is to look at, well, are there ways to parameterize the space so that we can parameterize kind of like the space of all the possibilities in the world? And can we sample this world very efficiently in order to create our tests, right? Because if you just sample at random, right, with all the variations, because don't forget that now it's not just about behaviors, it's about the appearance and all these different things of the world, right? Now the simulator can do so many more things, right, than anything else. So you need to make sure that you don't sample uniformly, but you sample so that you discover all the potential areas where you might have a risk or mistakes, right? And you can play with the adversary piece as well as in order to discover those areas very efficiently, as well as having a more probabilistic kind of estimate of how well you can actually do, right? So the idea is that you can basically start looking at, sampling a little bit and then refining your sampling so that you actually focus on the right thing. And then you can define what is the boundary of the things that you can handle versus the boundary of the things that you can't. And instead of running billions of simulations and then, burning, instead of on a real fleet, burning all your dollars in, Amazon or AWS or whatever your favorite cloud provider is, you can do this super, super efficiently so that your iteration cycle of your organization is a totally different dimension than before. All right, so just to conclude, I show you, I guess, Wabi World, and no more music. I show you Wabi World or some of the intricacies that we are embedding at the CVPR of how it works, how we can really clone the world in a way that is manipulable so that you can have this really next generation testing. And the thing that you can do here is that you can actually not just test, but you can train whatever piece, sub-piece, the middle, the beginning, the entire software stack on the simulator. All right, thank you.
questions? We don't really have that much time, but yeah, a couple of questions, all right.
Thanks, that was a beautiful talk. So, I have one question concerning the sensor similar close-up evaluation. So, for cameras, need also LiDAR, where there's a clear path between 2D and 3D. I think the simulation might work very well. But what about radar? So, do we have a solution to also mimic radar just about the nature of how the sensor works? Because if you don't have such a simulation, the close-up evaluation might be very difficult to do, right?
Yeah, if your system uses radar, you need to do radar simulation as well, so that you have a representation of the, of your entire sensors. There is other things that you can do, which are ways to bypass that. But in general, yes, we have publicly talked only about LiDAR and cameras, and that's where I will stop today. Yeah, but you need to simulate the sensors that you have on your vehicles.
Hi, thank you very much for this great talk. I have 3 questions, not more, but great. So first is quick. How much computing resource do you need to actually generate a scenario? Say, and how long is a scenario case?
Yeah, so the snippets that you see over here, I mean, typically, depending on what you're interested in, can range from, let's say, 8 seconds to 20 seconds. It really depends of what you're trying to test. And so, what was the first part of your question?
How much computing resource, say, GPU or CPU hours?
Yeah. Let's see. Did we have we talk about this in public? Do I have my folks here? Did we put numbers on the paper? Wait. Before you answer, did we put numbers on the paper? Okay, so this is what a couple of hours, right? For with Unison, a couple of hours. Now we have some other stuff that we are doing where you can do real-time rendering and some other really cool stuff, so that you can scale further. But this particular technique, yes, it's about 2 hours, something like this per scenario, for this the fidelity that you see over here.
Oh, okay, cool.
In one machine. Right.
And
so in the cloud, you can have thousands of scenarios very quickly.
Yeah. And also, I'm wondering if you have been using this for the closed loop training that you mentioned in one of the slides. Is it used for training or for testing only?
Yeah, so you can use for training or for testing. Yeah.
Okay, so then I wonder, if you do it in training, is closed loop training really necessary? Can you just do a perturbation in just one data sample? Randomly chosen instead of continuously.
Yeah. So for training the full autonomy system, is very important you have closed loop training. And whether you do RL or you do imitation like closed loop training, that's up to you. But it's very important that you understand the effects of your actions. There is some really exciting work also that we are doing on how you can combine imitation learning with real world data with, closed loop training, so that you get the best of both worlds. But yeah, it's very, very, very important. Like, well, you don't see that much this in academia because the metrics are just the wrong metrics. They're usually open loop metrics, which do not reflect the performance of the system.
That's great, thanks. And one last question. Regarding the agent behavior training, how do you measure how realistic it is, and how much realisticity do you really need for?
Yeah, so realism typically you can measure in terms of if you have a diverse enough data set, right? You can look at whether you cover well the space of the likelihood of some of your test examples that you don't use right in training. So you can do things like this. Yeah, so NNA, for example, would be a good way to measure this. You can look at whether your simulation results in collisions out of road, things that you will not see in real scenarios. You can look at coverage as well in terms of not just how likely things are, but is diverse enough so that you can handle all these things that you might see. So there is like different metrics, but in all honesty, there is a need for research on better metrics because those are not great. And yeah, so there's, we spend a lot of time thinking about, yeah, there are better ways to measure this so that we can optimize those other measures.
Thank you very much.
Thank you.
I guess we have time for only one more question. So sorry about that, but we can always ask.
Yeah, I was wondering for the self-driving vehicle perspective change, what's the sort of like maximum that you can make a change perspective? You showed some like lane changes, but you can make it do like a left turn instead of going straight, something like that.
Yeah, so it would all depend on what are the snippets that you use to create that world in the first place, right? So for example, if you're only going straight and it's a tiny snippet, you can't, at some point, you can generalize pretty well, but at some point you're going to see things that you've never seen. So it's all hallucination, right? So that's going to be very difficult to make realistic, right? And we've seen some great work in this conference, right? But it's still not this level of realism. What you can do as well is use more than one snippet to create that. And then suddenly you have your world, right? And then you can do more things.
But does this model have the capability to sort of like imagine the world?
This model, no, but you can do the things. Yes. And the same that you can, this model, this particular paper is only using one snippet, right? That's something that we wanted to show as, something is actually pretty challenging and very exciting, right? For example, if you have an intervention, you want to, yes, reproduce that log. But there are ways that you can combine more snippets, for example. And that's how you can expand these words.
Thanks.
And next we're going to have, which is going to be online.